can always, don't forget, those days I can always pick you up and take you so you don't have to travel. It's mostly just or you can just take the yeah.
All right, I'm here to talk to you about quantum computing today. So if you are in the room ready to hear some information that is useful, that you can use to start delivering value to your customers tomorrow, you're probably in the wrong room. We're going to talk about what on earth is quantum computing, and then will it break all my encryption. I linked to a lot of reference material throughout the slide deck. Rather than copying down every single link you see, my slides are going to be online at the conclusion of this talk. I'm going to turn them on at that point. So just copy down this one link here, https://speakerdeck.com/Craig Stunt. If you want to look up any of the sources, you can find them there. I'm going to be talking about some really weird, or at least highly unfamiliar stuff. So if at any point you feel lost during the talk, or you just want me to repeat something, you can just raise your hand or just yell at me, that's fine. I'm happy to backtrack. One of the really big advantages of a conference talk over reading about this stuff in like a book or a journal article is that you do get to shut me down and ask me questions, and I would encourage you to make use of that feature. When you look at the source material for learning about quantum computing, you see this big gap between like hand-wavy but wrong descriptions of what it is and correct descriptions that are mostly impenetrable to people who are not physicists or mathematicians. And they tend to be sort of punctuated with marketing that's designed to mislead. So I'm going to try and get somewhere in the middle there, and hopefully you can help me out.
Oh, I think you got it.
Sure. So why should anyone care about quantum computers at all? Well, one reason, there are others, but one reason is that we think they can do interesting things. We're pretty sure they can break RSA encryption. In fact, this has been demonstrated at a very small level on real quantum computers. And not just RSA, other kinds of encryption as well. So if you're here at a security conference, maybe that's interesting to you. But more constructively, there are processes in nature that appear to be inherently quantum mechanical, and if we want to simulate them effectively, it helps to have a quantum computer. Just for folks who maybe haven't encountered this term before, when we talk about a quantum, we're talking about the smallest unit of something. So if I talk about the amount of light in the room, I can measure that in lumens, and it's a floating point number, right? It's some value of lumens. But at the very smallest level, light is photons. And you can't get any smaller than that. You don't have a photon, you don't have light, so that is a quantum of light. And when we talk about quantum computing, we're talking about quantum mechanics, which are certain processes in nature that operate at those incredibly small levels, which do real computations in nature. It's not computations in the sense that we think of it, but we would like to harness these processes and use them to do computations that are more useful to us. So the equations of quantum mechanics provide a way to calculate the properties like stability and chemical reactivity of a molecule such as a drug, but we have not been able to solve these things classically without making a lot of simplifications, which is why you have projects like Folding at Home and stuff that attempt to use massive computing power to solve some of these problems. But we're looking for a better way to solve the problems. Also, there's good reason to believe that quantum computers may provide an exponential speed up in certain calculations commonly used in training machine learning models. However, you may have noticed that TOS does not appear to be broken. And there's an adjective you'll hear, which is a cryptographically relevant quantum computer. We'll talk about what that means in a little bit, but the simple version is that we do not yet have real quantum computers that are big enough to break the strengths of the ciphers that we're using today. So yay, you can continue to shop Amazon and stuff. And even maybe a more general point, which is that currently we can simulate a quantum computer in some degrees faster and more effectively than we can build a quantum computer. So we can run a simulation of a quantum computer on a big classical computer, and we often actually get better results doing that than on the real quantum computers that we've built. So there's this notion of quantum supremacy, which is that at some point we are likely to be able to build a quantum computer that cannot be effectively simulated classically. But that hasn't happened yet. Another really interesting thing that's going on right now is that as algorithm designers and complexity theorists attempt to prove that there are certain things that can only be done on a quantum computer, every now and again they find a way to do it on a regular classical computer, which is neat because you can walk into Micro Center and buy one of these classical computers. So we've actually been making a lot of progress in classical algorithm design as we study how you might implement an algorithm on a quantum computer. And even if you did have a very big quantum computer, you can't just throw TurboTax at it. There are certain things that it's good at and certain things it's not so good at. It's not a universal speed up. I tend to think of these things as like a domain-specific coprocessor. So what is it that quantum computers do well? Interestingly, we're not sure. That's not just about quantum computers, right? We don't actually know, in many cases, what a classical computer can do well. So we know that there are certain problems that are very hard to solve on a classical computer. We know that there are some that are probably impossible in the general case. But for many problems, it seems like future progress might be made in algorithm design, right? And for a large subset of the problems we're interested in, we don't actually know what an optimal algorithm looks like. So this is a profound question of computer science, and it's very, very relevant to folks designing encryption algorithms, is what exactly is hard for a classical computer to do? What is hard for a quantum computer to do? The set of problems that we're interested in of cases where we actually know how hard they are is actually a lot smaller than you think. Which on one hand means, okay, great, there's this opportunity for improving algorithm design, that's great. But on the other hand, in cases where we really care, and encryption is one of them, in cases where we really care, that we know that some problems are hard and it is hard for the bad guy to figure this stuff out, we don't always know that to be true, which is why it takes a long time to vet new encryption algorithms. And another issue that just keeps coming up is that when you look at articles in quantum computing in the popular press, a lot of them are just marketing. Having said that, you should probably care anyway. The advantages are potentially huge. And a big problem that weighs a lot on my mind is that new cryptosystems take a long time before we're confident in them. I mean, just as an example, public key cryptography was invented in 1977, maybe, probably. RSA debuted in 1988. PGP was released in 1991 and SSLv2 in 1995. So it could take 20 years to gain confidence in a new cryptosystem. If a big quantum computer makes RSA obsolete overnight, we better have something in the cooker warm enough and getting ready, right? So this is a problem that we're concerned about today. Another interesting thing is there are physicists and serious people, not cranks, who will assert with all confidence that a big quantum computer can't be built. In which case you might say, well, why am I bothered talking about this? I suspect they're not right. However, even if they are right, it's really interesting because we would need new physics to prove that's true. Okay? So one way or another, the deeper we look at this, the more interesting the subject gets. So a term that I just wanted to define, because you'll hear me throw it around a lot, is a classical computer. This thing that's showing the presentation is a classical computer. I have another one on my wrist and in my pocket. Pretty much any computer you can go into Micro Center and buy today, that's a classical computer. And we just use that in contrast to, you can think of it as a non-quantum computer, but classical computers is the term people use. Doesn't mean that they're bad computers, they're just different. So when you read about quantum computing, you're often confronted with a bunch of math and physics. I mean, like at least ones who pulled the marketing filler out of the articles. So you might wonder, like, how much of this do I actually need to know? And it depends on who you are. It depends on what you're interested in. If you're a software developer, then you don't really need to know a ton of the math and physics. You can just think of this thing as something that it's a device that executes certain tasks fast. So if you ever program to a GPU or to a DSP, you don't really need to know like the mathematical details of how those things are implemented. You just send your code there, maybe written in a special way, and you know it runs the thing fast and very productive. If you're a cryptographer, however, or writing a library for one of these devices, you're going to have to know a lot of the math, probably all of it. And if you're a hardware designer, you need to know all the math and all the physics as well. Okay? So just figure out which bucket you fall into there, and that's pretty much what you need to know. So we often think of our computers as being general purpose, but in fact they contain some special purpose devices, and I've given you a couple examples already. One of the first computers I ever purchased was an 80286, and it had this slot next to it for the 80287 math coprocessor, and you buy it separately and drop it in the slot, and then your Excel sheets would all populate faster. So one way that you can think of quantum computing is it's just another kind of coprocessor for certain tasks that quantum computers can do well, because quantum computers, as far as we understand them today, are not general purpose, and you need, even to run a quantum computation, you probably need a classical computer to do some pre-processing and some post-processing on the data that you use. So it's just another specific device. And also, quantum computers tend to be located in data centers. You're unlikely to have one like on your iPhone anytime soon. Because we are looking at individual particles, and because interacting with the particles, which can include heating them, means that you destroy the quantum state, what happens is these computers are typically like, maybe this big, and they're surrounded by a room-sized refrigerator that cools the thing to absolute zero. So not going to be in the Apple Store next year or the next decade. Okay, so going further along in this sort of coprocessor angle, one interesting thing that's happening is you may have heard about the end of Moore's law. As the overall increase in transistor density, which interestingly is limited by quantum effects, and clock speed of CPUs is tapering off, there's pretty good reason to believe that we're in the midst of an architectural shift from general purpose computing devices to application-specific accelerators like tensor processing units and things, application-specific integrated circuits, and this notion of having dedicated silicon for certain purposes may actually be, for the near term, how we get a speed up if we can't make our transistors any denser than we currently have. So let's look a little bit at just kind of architecturally how these things might work. So first I'm going to just talk a little bit about how classical computers work. Many of you are familiar with this, so just bear with me as I give a quick refresher here. For a classical computer, we typically have input, and sometimes the input comes from main memory, sometimes it comes from an external device. We're going to load some of those values into registers. A control unit is going to step the computer through the program where certain combinatorial logic like add or XOR or things like that operate on the register, and then we copy that either back to main memory or to the output of the computer. Does that all make sense? Okay, I see a few notes. Usually as a software engineer, we're not working at this level because compilers do it for us. But if you're reversing, you may actually be looking more at this level, okay? And this is the level that quantum computing changes. Here we go. So here's what your program might look like there. think I've lost the battery on my remote, so I'm just going to step through here. And what are these registers? They're just little banks of ones and zeros that are all grouped together. You can think of them kind of like switches. Each one, has a value that's on or off, and we can look at the value in the register and we can know what it is. That's kind of unsurprising. So a particular type of computer, a quantum computer that I'm going to sort of show by analogy here is called a quantum gate array. There are other types of quantum computers that are under development, but I'm going to use the quantum gate array as an example here because it looks really similar to a classical computer. The input and the output in this case, it probably actually is a classical computer. And instead of registers, we have qubits. And instead of combinatorial logic, we have quantum gates. And instead of assembly, we build circuits. And again, as the programmer of a quantum computer, as the designer of a quantum circuit, you might not actually work at this level. You might work in a higher level language and have it compiled down to here. And if this seems a little odd, don't just hang on to that for a sec because we're going to dig in a little deeper. So what are these qubits? Instead of having a fixed value of on or off, the qubit has a property called amplitude, which you can think of as roughly the probability that it has the value 0 or the probability that it has the value 1. And actually we take both of those and we sum them together. So you could roughly think of it as there's this hidden internal state that is either 1 or 0 that we can't see and has a certain probability. However, a lot of physicists don't believe in the internal state model. Okay? But what we can say is that we can, not only can we know the probability that the state of the qubit is 1 or 0, but we can also assign that. So if I want to say this qubit has the 100% probability that the value is 0, I can slide that lever all the way down. Okay? And then I can do operations on that lever. So the quantum operations then look kind of like this. We take certain qubits, we perform a quantum operation on them, and then we get something that actually we don't know. Okay? All right? However, we can open this safe, and we get one possible value according to that according to that probability distribution. Okay? So, and I'll give another example of this going forward. Okay? Now this seems sort of useless, right? Because if we take these known values and then we perform an operation and we get, okay, there's a probability of what this value is going to be, and I can get one value on that probability curve, that seems maybe a little bit useless. Okay? Random number generators are useful themselves, but it might not be the answer to our problem. So what we'd like to do instead is we want to increase the probability that the value we pick is the correct answer. And that's really useful right here. So here's a more specific example. We could start with the qubit set to the value 0. And again, we can assign these qubits. So I can set 100% probability that this qubit is 0. I can perform some quantum operation on them, and then the value that I get out is going to be either 0 or 1, and you can see the multiplier here in both cases is 1 over the square root of 2, okay? Since that's the same value, I have equal probability in this case of it being 1 or 2, okay? And again, this probably seems sort of useless in terms of breaking encryption, but does what you see here on the screen at least make sense? I start with some known value, I do a quantum operation, and then I get some unknown value, and when I finally read this thing out, I get to know if it's 1 or 0. Are you with me so far? Okay. So I'm going to measure this thing, and it turns out to be 1. Okay. So how does that get us to actually solving real problems? I have included cartoon panels in my talks in the past, but it's usually for laughs. This one actually is the single best explanation and the single most concise explanation that I've seen over how this actually works. What we're going to do, and I'll just read this out loud here because it's a little dense. In quantum computing, the whole idea is to choreograph a pattern of interference where the paths leading to each wrong answer interfere destructively and cancel each other out. well, the paths leading to the right answer reinforce each other. So I'm going to change that probability curve to get something that is hopefully the correct answer. Okay? This is the essence of why quantum computers have the potential to be so fast, but it's also why programming them at a low level is so unfamiliar. So you can make an analogy to things that you see in the non-quantum world. So the noise-canceling headphones is one analogy. We're trying to preserve the signal we like and reject the noise from the outside. Another example are when two waves intersect. This is a real example of that phenomenon. What we find is that at some places the waves reinforce each other, and at some places the waves cancel each other out. So, like another analogy for this is when you're on a swing set, and you kick in time with the swing, you go higher, and when you kick out of time with the swing, you go lower. We're trying to constructively reinforce the correct answers and destructively cancel out the incorrect answers. Another thing that we have to cope with is noise, and this is not new. It's not new for quantum computers. Classical computers have to deal with this as well. Classical computers are interfered with by cosmic rays, by resistance, and also by quantum effects. If you try and build a transistor that is smaller than 7 nanometers, you'll find that electrons will tunnel through the gate oxide layer, okay, and that's a quantum effect. But we've gotten pretty good at making classical hardware more reliable with redundancy, with hardware and software noise correction. We have a similar issue in quantum computers, but it's harder because when we're dealing with individual particles, like an electron, it doesn't take a lot of heat in order to introduce noise in that electron, okay? Which is why you have these room-sized refrigerators around. But even with that level of isolation, it's still really hard to when your definition of noise is so sensitive, it's really hard to deal with that. So what do? What engineers are doing mostly right now is using some redundancy, taking these qubits and using them in a redundant way to try and remove the noise. But there are other approaches that I'll show you in a little bit. But one term you may see are physical and logical qubits. So a qubit is a measure of the amount of data that you can work with in a quantum computer. So the quantum computers we're building today are anywhere between like 7 and the biggest that I've seen, with one exception, is about 120 qubits, but the largest definitely quantum operation that I've seen has been about 30 qubits, which is pretty small. So when we talk about physical and logical qubits, a logical qubit is where maybe you've chained multiple qubits together to deal with noise. So the physical qubits is the number of physical qubits in the quantum computer. The logical qubit is the computing capacity once you've taken out the factor of redundancy for noise correction. So this is a kind of a theoretical topic, but it's really important here. So as I mentioned before, we don't actually know what problems are hard, with a few exceptions. So I want to talk about computational complexity theory. So there are a few cases where we believe that a general solution to the problem is impossible. So we know from Turing that on a classical device anyway, it's not possible to build a program that looks at another program and decides whether it will terminate or not. Turing proved that in the 30s. There are cases where the solution does exist, and unfortunately it is difficult to compute. It's exponentially hard with the number of nodes in the problem. We care a lot about some of these things, so besides the traveling salesman problem, there's Sudoku, the protein folding, Battleship, Pre-Cell, Mastermind, Tetris, Minesweeper, and creating crossword puzzles are all things that are considered NP complete. On the other hand, some problems are pretty easy by comparison. So we've known since Euclid that there's an efficient algorithm for the greatest common divisor. And then sometimes we're not sure, and complexity theorists say this a lot. The whole strength of RSA encryption, and I'll go into details on this later, is based on this idea that it is difficult to take some very large number and figure out what its prime factors are. We believe this is true because we've worked really hard on the problem and we haven't been able to solve it, but it is very much not proven. Okay? And we know that with a quantum computer there is actually a more efficient solution to this. So the knowing which problems are efficient on a classical computer and knowing which problems are efficient on a quantum computer is an unsolved problem of profound importance. And just an example of this, there's this problem called the recommendation problem. It relates to collaborative filtering and machine learning. And so if you've gone to like Netflix and Amazon, they're going to look at what you've looked at and decide, you know, here's some other things you might be interested in. And you may have noticed it doesn't work very well, especially if you're looking at like your Amazon recommendations. It turns out that this is really hard to do well on classical hardware. Now, it's known since 2016 that a much more efficient quantum solution exists. And this teenager who was interested in complexity theory reached out to Scott Aronson and said, what are some problems that I can work on? And he said, well, prove that that there's no better classical solution for this problem. He worked at it real hard. He came back to Aronson and said, I think I found a classical solution to this. Aronson looked at it and said, yeah, I think you did. The interesting thing here is that he would not, probably by his own account, have found this new improved classical algorithm if he hadn't been inspired by how the quantum algorithm works. So there's this back and forth right now where we're learning a little bit what classical computers can do efficiently and what we think. As far as I know, there are very few problems where we believe that only a quantum solution could exist and a classical solution can exist. It's much more common that we just don't know. So the point in all this is that the line between what a classical computer can do efficiently and what a quantum computer can improve on is not at all clear. So here's another view of this. In this diagram, we're going to show the relationship between some of these complexity classes. NP-complete are the exponentially hard problems from the previous slide, and P are considered the easier problems. And then there's this other class here called BQP, which is bounded error quantum polynomial time. And the definition of this thing is these are the problems that can be solved by a real-world quantum computer easily. And the problem is that given that definition, we're not sure what's in it. So this is one person's guess at where these things fall, but we don't actually know with certainty that NP and P are separate. If you can show that they're separate, you win $1 million, by the way.
So the BQP field extends into both the P space and NP space. Is that on purpose?
Yes, it's definitely on purpose, because if you think about a problem like factoring large primes, we think it may be in NP. We're not sure. Okay? It's definitely in BQP. And it's probably not in P. Okay? That makes sense? Okay, so let's look at how we might build and program a quantum computer. One of the things that quantum computers definitely do really well are Fourier transforms. A Fourier transform is an algorithm where you can look at a wave, like a piece of audio, and you can decompose it into the fundamental notes that make up that wave. Okay? It's something that is somewhat difficult for a classical computer to do well. You can sort of pick out one frequency at a time and do this on individual frequencies, but to do across the whole spectrum at once is difficult for a classical computer. Quantum computers do it really efficiently. And one term that you may see in press articles is NISQ. These are noisy devices with a small number of qubits. And this is the term that John Preskill, who's a quantum computing theorist, has assigned to basically the quantum computers that people are building today. Noisy intermediate scale quantum. These are the computers that have a lot of problems with noise and have, say, less than 50 qubits. So I'm going to show you 4 possible architectures for a quantum computer. So I talked a little bit about what a qubit does, but the question is, how do you build one of these things? So we want some sort of thing where we can assign it the probability of being in one state or the other, and we want to be able to read it out later and get a value out. So how do you actually build one? We do see these effects in nature, but nature is not an effective way to do arbitrary computations. So, so one way is that you can take an ion, which is just a charged particle, and you can suspend it in space, and then your qubits are based on the electronic states of the ion, such as a ground state versus an excited level. And there's one company called IonQ that has built a computer based on this, but there's a lot of academic researchers who have built non-commercial ion trap computers. IonQ announced last week that they've been able to do a full quantum computation on 30 qubits out of 160 that are in their device. That is a very impressive result. They seem to be making a lot of progress here. I presume this holds up, yes.
Do the electron states represent the qubits in that law?
Yeah, it's the excited state versus the ground state. So in the ground state, there's no charge. In the excited state, there's a charge.
And there's a variableness to that charge that represents the different amplitudes of the qubit?
Well, it's quantified. So we have to be careful when we say variableness. The charge can either be none, or it can be a negative charge, based on where the electron happens to be. And generally, we're only interested in those two. There's no in between. Okay. More common in commercial quantum computers are computers based on superconducting circuits. So, for example, you might have a loop of superconducting wire, and you might measure the amount of magnetic flux as the electrons travel around that loop. This is used by IBM, Google, Rigetti, and others. Real hardware does exist, but it's pretty noisy, and the qubit counts are low. I think IBM has a device with like 17 qubits that you can use for free in their clouds, and it's based on this kind of architecture. One that you may have heard a lot about is called quantum annealing. There's a company called D-Wave that makes these devices. They claim 512 qubits, but it is not apples to apples. Instead of building quantum circuits with gates like the architecture that I showed you before, the way the D-Wave computer is basically hardwired to a single problem, which is Boolean satisfiability. That is a very interesting problem, and it's one that's hard to do well. In the classical world, we have solvers like Microsoft Z3 that do it okay. But from the number alone, you might think, 512 qubits, that should demonstrate quantum supremacy. In fact, D-Wave has never done a computation that we have not been able to simulate classically. So there's a lot of debate over what these computers exactly are doing. We're not 100% sure, and neither is D-Wave 100% sure. But it is something that they're building, and we're trying to figure out what these things do. It's certainly a less flexible model for computation. It might be interesting if they build something that we can't simulate classically, and they may get there, but it doesn't solve general problems. Yes?
So with a few of these examples or models that you presented, you referred to them as being noisy.
Okay, yeah.
Do you mean what do you mean by that?
I mean that you get incorrect results, and the reason that you get incorrect results is that you get some infinitesimal tiny bit of heat that goes and messes with your electron. That's noise. And, like I said, if my phone overheats, I'll get incorrect results. I'll shut down and reboot, right? But it takes a lot of heat to make that happen. If your qubit is a single electron, then it doesn't take much heat to make that happen.
So that tiny amount of heat is just the right amount of heat to knock out.
Mm-hmm. Yep. And really anything that interacts with the particle at all, it could be heat, but it could be any kind of interaction at all. Interaction is a sense of measurement that makes that quantum state go away. Okay? So Microsoft's approach to quantum computing is interesting. This is Microsoft research. If successful, this would be noise-free, essentially. which is a huge advantage. The principal drawback of this approach is that it's based on particles or quasi-particles that many scientists think don't exist. Needless to say, Microsoft has not actually built a physical device. The particular particles they're working with are called non-abelian anyons, and there is some evidence to suggest that they do exist, but we don't know how to build one into a computer yet. But if this was successful, it would be really interesting because they're really not susceptible to noise in the way their architectures are. So it's an interesting area of research. It's nice to have companies that actually do this kind of peer research, but we'll see where it goes.
Question?
Yeah.
If it's not susceptible to noise, then how do you make measurements?
Any particle in a quantum state can be measured, at which point it's no longer in the quantum state.
Right, but usually, like, we observe it with a photon or something like that, which basically equates to noise, which collapses the quantum wave. So,
I would dispute that it exactly equates to noise, because in the noise we don't get the measurement.
Well, it's intentional.
Yeah.
But
So it's the difference between getting the measurement out or not. Like, okay, you can collapse the quantum state with noise, or you can collapse it with measurement. In either case, you no longer have an end of quantum superposition.
Right.
However, in one case, you get the value out, which is useful.
okay.
Okay, so what's it look like to program one of these things? Microsoft has a research language called Q#. Needless to say, since they don't have physical hardware, you have to run this on a simulation. But it's sort of interesting because this is roughly the assembler level of programming a quantum computer. You execute a Q# program by wrapping it in a C# harness. And the C# harness represents the classical input and output for the computation. So in the same way that you would have a physical classical computer feeding the quantum device and reading the values out, that's C# in this language. And then in Q#, you have the quantum effects. So here we set 2 qubits in some initial state. One we set to 0, one we set to some value that we pass in. Okay. Then we execute 2 quantum gates. The H stands for Hadamard, and the C0 stands for C0. These are just, think of them like XOR and add. These are just two things that you can do to a qubit. Okay. And then we use this M function to measure the result, and then we act on the measured results. So, okay, that's actually not too hard to read as code goes, but when I look at this, I really don't understand what this thing is doing. Okay, what this thing is actually doing is it's demonstrating a Bell state, which is very interesting if you are a physicist, but as a computation, it's not particularly interesting. It's like I just showed you how an adder works. Okay, great, I can add 2 numbers together, whatever. The point is that we're working at a level that's possibly interesting to microcode library designers. We're not really at a point where this is super interesting to programmers who are trying to solve business problems. We need lots of work to do that, but let's move forward and let's talk a little bit about some problems that we could solve. And so the crypto thing. This is probably the thing that's of most interest to folks at BSides. I have a couple of preliminaries to go through before I talk about how you can break RSA with a quantum computer. One is this. There's a popular myth that what a quantum computer does is it tries every possible input and every possible output at once and tries them all and then instantaneously selects the value that is correct. That is just simply not true. It's a wrong statement, and quantum computers don't work that way. Okay, so how does it work? Well, in order to talk about, there's an algorithm called Shor's algorithm that can break RSA. But in order to talk about how that works, I need to talk a little bit about how RSA works. This is a very rough overview. I'm going to take some liberties with the math here. But if I give you 2 numbers, it's pretty easy to find their product. You take out your calculator or do it in your head and you multiply them together and you're done. But if I just gave you this value like 221, it's not even a very big number, even with a calculator, you might find it a little bit of work to find out, what exactly are the factors of this. But if I told you that 13 times 17 equals 221, you could check that really easily, right? Okay? So, very, very roughly speaking, if I give away the product of two pretty big numbers, you're going to have a hard time figuring out what those numbers are. So you can think of, and this is not correct, but it's close enough, you can think of the product of those numbers as the public key and the individual factors as the private key. Okay? That's not entirely accurate, but it's close enough to show you why RSA works. So, in order to break RSA, I need to be able to take one of these very large numbers that's the product of two very large prime factors, and I need to factor it into the two very large primes that were multiplied together to make it. Okay? I don't know any of them yet. One other concept I want to make sure you understand is this notion of a period of a function. Okay? So this function is the sine, which you might have encountered in your trig classes, and the input to the function is the horizontal axis, and the output of this function is the vertical axis. So what you can see is that the output repeats. Okay? If I go from negative 2 pi to 0, and then from 0 to 2 pi, the output of the function repeats. And in fact, it will do that forever. Okay? So the period of this function is the amount of input space over which it repeats, and in this case, it's 2 pi. Is that clear? Okay. Now, it is pretty easy if I tell you that the function is sine, that you can tell me what the period of the function is. Any high schooler who's taken a trig class can do that. If I give you some black box function and say, I'm not going to tell you what this thing does, but please find the period of it, you're going to have an incredibly difficult time with that. Like, I don't know a general solution for it, at least in the classical world. Okay, so how does Shor's algorithm break RSA? Like many quantum computations, there's both a classical part and a quantum part that's required to get a useful answer. So first what we do is find the greatest common denominator of a couple of numbers, one of which we sort of choose, and it's a pretty simple classical computation to do this. And then we get to the quantum part. We take those answers and we build them into a function, and we find the period of the function. Well, I just told you it was really hard to find the period of just any general function. However, if you have access to a quantum computer, there is an algorithm to do it. Okay? And then finally, we do a little bit more very simple arithmetic. And it turns out this works in the real world. So somebody took the number of 15, plugged it into a quantum computer that it was implementing Shor's algorithm, and they got 3 and 5 fell out of it. Okay? Well, that's interesting because it does show us that we can use it, that the algorithm does work on real hardware. Unfortunately, it's not quite good enough to get us to break TLS, right? But despite these small numbers, Shor's algorithm clearly works. So actually, let me back up just a second here. Basically, what we've done here is that we've taken one hard problem, which is factoring the product of two large primes, and then we've used some pretty simple classical math to change this into another hard problem, which is finding the period of an unknown function. It just so happens that there is a quantum algorithm for doing that. Yes?
Earlier, if I'm understanding correctly, earlier you were saying that we have physical quantum computers with physical bits like 128, logical like 30. So I gotta think 32 bits would be sufficient for Shor's algorithm to break modern encryption. What am I missing?
You're just off by a little bit,
Okay.
So it's more like thousands of qubits.
Okay.
So if you think of the primes that are involved in a modern cryptosystem, we're dealing with like 2048 bits. Okay? So you're not entirely off. It is just a question of scale.
Yeah.
That's all it is. But the scale that we're looking at is like 10 times the size of anything that we've built.
Okay. Okay.
And these things do get exponentially harder to build as we try and couple more and more of these qubits together. So I believe it's a solvable problem, but getting us to the point where we can actually break modern cryptography is just a considerably bigger computer than we've ever managed to build so far. Okay, so I mentioned earlier that you can't use a quantum computer to simply try every input and every output to a function instantaneously and pick the right one. That's called a search problem, and Shor's algorithm does not use a search approach to the problem. It uses this special period finding ability. However, quantum computers actually do help you with search problems, just not as much as you might like. Okay? And yeah, I somehow went a slide further than I intended to. Okay, here's the slide I intend to be on. So unlike Shor's algorithm, which is only useful for finding the prime factors of a large composite, Grover's algorithm works with general functions, and it does help with a search problem where you're saying, please show me the inputs that would cause some output to be true. It's just not instantaneous. So the big O notation is O to the square root of n. That's still an improvement over the classical, so that the classical version of this is O(n). You simply try all the inputs and pick the correct value. O to the square root of n is a much faster algorithm. And it is still true that we're not instantaneously just picking the right answer, but there is some improvement available for a search problem. And, you know, again, this is not really useful for cryptography because the numbers we deal with are so big. But it's useful for other problems. Okay, so as I mentioned earlier, it might take 10 to 15 years to gain confidence in a novel cryptosystem, so it's really important that we work on new public key cryptosystems right now. Most of the symmetrical algorithms like AES that we use today, it seems like they're okay. Again, you have to use some care because we're not precisely sure what quantum computers are good at, just like we're not precisely sure what classical computers are good at. But it seems like AES is likely to be quantum resistant, but pretty much all of the mainstream asymmetric, the mainstream asymmetric cryptosystems seem to be vulnerable. Let's put it this way. We can't prove that they're not vulnerable to a quantum computer. Okay? So NIST, the National Institute of Standards and Technology, is having a contest right now to come up with a new cryptosystem that is not vulnerable to quantum analysis. So some of the contestants in this cryptosystem are using techniques like learning with errors and the shortest vector problem. Chrome temporarily shipped in 2016 with a couple of experiments of quantum-resistant public key encryption. Those have since been removed from Chrome because the experiment is done. And here's one interesting thing. Some of the experiments have failed. GCHQ had published a quantum-resistant public key cryptosystem called Soliloquy, and then they, a couple years later, they published a paper called Soliloquy, a Cautionary Tale, which is interesting reading if you go find it, where they decided, you know what, we think this cryptosystem is not actually, we think it's a good cryptosystem, but we think it's not actually quantum resistant. And because its whole point is to be quantum resistant, they stopped work on it. So, how close are we? And this is kind of the question that you were asking. So there are a couple of milestones that are interesting. The first one is called quantum supremacy. We have not yet built a quantum computer that is big enough that we can simulate it classically. So a fancy laptop, you can simulate like 29 to 30 qubits. If you have access to a supercomputer, we're trying to, you know, it used to be like 45 qubits. Some developments in supercomputing have pushed that to like 50 or 51. But each time you add another qubit, you're doubling the effort to simulate it. At a certain point, like, what's the point, right? Like, okay, we could get to 60 maybe, but if we can build quantum, there will be a point where we can build quantum computers bigger than what we can simulate. In order to make RSA obsolete, we have to have thousands of entangled logical qubits. That is a threshold that right now we don't even have a horizon for, but speculatively, a lot of people say 5 to 10 years, some people say 10 to 20. It's going to be somewhere in that time frame. You'll note that's probably just enough to vet a cryptosystem to replace RSA. There's probably just enough time to finish that NIST competition, to gain some confidence that not only does the cryptosystem work, not only is it like maybe not breakable classically, but just as we learn more about what quantum computers can do, to say, oh, this thing really is resistant to quantum analysis or not, and then to say, okay, if we believe the cryptosystem's good, what about the implementation? Probably just enough time in there. If you're interested in learning more about the topic, yeah.
If you say there's just enough time, there's no way we're going to get it done then. just because of humanity. So what's your level of confidence there?
Well, there are a lot of unknown unknowns here. Okay, so it's just enough time if the speculation about when we build a cryptographically relevant quantum computer proves to be correct. If it's incorrect one way or the other, well, okay, so what if we build a cryptographically relevant quantum computer next year? Well, then we probably have to deal without asymmetric encryption for a while. Was that
4096 bits or 8192?
Yeah, maybe we can scale it bigger, maybe.
It make things a lot slower, possibly, but...
Yeah, I mean, it's an interesting question about if RSA and elliptic curves didn't work, what would we do? And where doesn't work is defined as the bad guy can decrypt it.
But the other thing is, too, that it's expected that there would only be mostly nation states that would have these facilities at the beginning.
I don't know.
At the beginning.
Yeah, it's hard to say because they don't talk very much.
Yeah, I mean, they have other easier ways to listen in.
So the conspiracy theorists among us will assert that NSA already has this. Doesn't strike me as credible since NSA puts so much work into other means of breaking RSA, but it's conceivable. But, we could be wrong in the other direction, right? It could be 30 years or 50 years, right? Okay? So basically, I think it's good to work on these things because at some point I do believe it will be a factor. At some point I do think that we're going to need something different.
We put these devices in space someplace that's a little colder and everything else. Can we speed up this timeline?
You can go a long way with this. There's a whole field, and if you're curious about this, called hypercomputation, which is, well, I have this computation that takes a long time, but what if I sent the computer into the event horizon of a black hole? And
I was like,
so it's actually a really fascinating
kind of hard to get to.
So unfortunately, space is not cold enough. We're talking about fractions of a degree above absolute zero, and when I say fractions, I mean really small fractions. There's also a lot of radiation in space that's problematic, but you're thinking outside the box, which is good. Like it's those types of like, well, what if we did something?
I think AWS is coming out with a release.
Yeah,
They would put refrigerators in space, but the extension cord is too long.
Instead of moving everything to the cloud, we're going to move everything to orbit.
moving it into the Ur cloud or something. Okay, so I have a list of references here. I'm going to go. I think people are starting to move. I'll go real quick through them. Here's a really simple introduction to programming with Q#. It's an easily readable blog post. Again, just skip the deck rather than copying all these down. Quantum computing in the NISQ area and beyond is a great overview of where we are today in terms of what the machines we've built today can do. It's about 50 pages. Quantum Computing Since Democritus is a more mathematically intense book that looks at the topics of computational complexity. Quantum Computing Progress and Prospects. It's kind of like the NISQ era and beyond, but it's about 300 pages and it comes from the government. So it's just a little more detail. Here's a real quick blog post about the experiments in Chrome that the Chrome team did. And then a couple of the articles that I referenced during the lecture here. One other thing that you can do is you can reach out to me personally. I'd be happy to come and chat with your team if you'd like to, or just, we can have coffee or whatever. I live in Columbus, and I'm easy to reach, so do feel free to reach out if you just want to talk about this some more. I'm happy to talk until the next speaker comes in, but it looks like people are
here.
The
next speaker's here.
Okay, excellent. Okay, I'm going to give you time to get set up. Thanks for coming out. Also, this is the first conference I've been in this talk at, so I really could use your feedback. If you just